All right, hopefully everyone's doing fine. This is the final lab recording that I hosted last week. This is a video recording for the people who weren't able to attend the lab or they had any questions during the lab. So the plan for this video is going to be pretty simple. I will give you guys, well, I don't need to give you guys any time since you're watching. I'll show you guys the question. Make sure to pause the video, read the question on your own. And if you're able to understand the question better and solve it on your very good, that means you're ready for the final. If not, that's fine. I'm going to decipher what the question is asking us, and then we'll figure it out on our own, right? So hopefully you paused the video and read the question. If not, let's just go into it. Okay, so let's understand first what the question is asking us. The question is asking us that we're given two separate tree data structures in the scenario. In this scenario, they are called P and Q. What we need to check is we need to check if P is equal to Q. So how can we consider P equals to Q? First of all, the structure has to be the same, right? The structure of these two trees has to be same, and the values, and the values have to be the same, right? So in this case, you guys tell me, looking just by looking at it, are P and Q equal? Yes, they're equal, right? Because P, the structure, look, one node, one node, one node, one node, one node, one node. So the root node has a left and a right child. The root node has a left and a right child, right? So this is the idea what I'm trying to do. So the structure is same, and the value stored within each node is same. So look, root node has one value, root node has one value. If you go to the left child, has two value, has two value. If I go to the right child, three, three, right? So the values and the structure, they're both identical. So I can safely say that P is equals to Q. So this is one example. Let's take this example. The structure is the same, right? So the structure is the same, right? So the structure is the same, but the value stored within each node are different, right? So like, look, root node checks out, has a left child, does not have a right child, does not have a right child, that checks out. But the values stored within the left child are not equal to each other. So I can say that what? These two structures or these two data structures or these two tree data structures are not equal to, sorry, can I use my pen? Not equal to each other, all right? Now the third problem, now the third test case, sorry. Look, the structure is different here. Like, look, P and Q have a root node, with the value of 1, right? But P has a left child with the value of 2, and Q has a right child with a value of 2. The values at each level are kind of same, but the problem here is the P has a left child and Q has a right child, right? So this is the case where I can also safely assume that, not assume, I can say with that P and Q are not equal to each other, right? So this is exactly what the question is asking. So how are we going to solve this, right? So for this question, you might think a couple of base cases in your head. So let's talk about a couple of base cases. Then we'll talk about the recurrent solution or the recursive part for then later on. So the first base case, I need to obviously check what the value. If the value in P, the P's value does not match Q's value, right? This is a false, right? If this happens, that means I need to return the value of 0, obviously, right? This pencil is not working. I know it's gonna. So I need to return the value of 0 because the values at each node, they don't match. But before I do this, I need to check if I'm dereferencing a null pointer, right? If I do this, what is the problem with this? The problem with this that P could be null, Q could be null. So then that my code would result in a segmentation fault because I'm dereferencing a null value, right? So I need to check if the nodes are valid or not. And that will also in turn help us verify that the structure is the same, right? So look, so the first base case would be if P is null and Q is null. You guys tell me what does this mean? Oh, well, I can't not hear you, but think of it in your head. If P is null and Q is null, that means both of the pointers are null, right? So this is, if they're both null, that means this is a valid, they're both are the same. So I can return the value of 1 back to the function, right? Okay. Another test case, another base case would be if P is null or Q is null. So what does this mean? Either one of them is null. Look, this checks if both of them are null. If both of them are null, I can return the value of 1 as in true. If one of them is null, if this is null, but this is not null, that's why I'm using the OR operator, means, right? That means return the value of 0 because one is null and the other one is not null. So stop here, as in like these two trees are invalid. Now the third base case is if P arrow val does not match Q arrow val, right? This means again that these are two different structures or different different two tree structures. This is like a word puzzle or something, tongue twister. Sorry. Okay. Now these are the base cases, right? 1, 2, 3. Now we need to figure out the recurrent solution part. Now look, let's go through the diagram first. Now look, ask yourself. We have learned some traversal techniques in class, right? We have learned pre-order, in-order, post-order, and these are called what? Depth first search traversal techniques for a tree. You will also learn them in CS2, but this is what we have learned. Depth first search traversal techniques. Now ask yourself, if I go left on P, do I also need to go left on Q, or do I need to go right? Right? I'm checking the two tree structures are the same or not, right? So if I go left on P, obviously I need to go left on Q, right? If I go right on Q, I need to go right on P. If I go right on P, I go right on Q as well. So this is how the traversal would work. And the recurrent solution would be what? P arrow right, comma, Q arrow right, and the reason I'm using the AND operator, because both of my decisions have to return the value of 1. If one of my decisions, look, like in this case, let's take this case. I go left here, I go left here, right? Now look, this is fine, but this is not fine, right? So this will return the value of 0 back to the last caller. So this means that my whole tree structure is wrong. So this is why I'm using the AND operator. If either one of my decision returns the value of 0, that means my whole answer is wrong, right? So short circuit to be a false, right? So again, if I go, let's do this again. Sorry, the writing is not too good. I will also be like uploading not uploading the code for it, but actually, yeah, I'll be uploading the code for it, so you're able to view it. So look, P arrow right, comma, but left. Sorry, we're using depth first search, right? Left, comma, Q arrow right, the function call of, and the function call of P arrow right, comma, Q arrow right. So yeah, I won't be coding in this video because I just want to explain the conceptual part, but the code is provided to you within the zip file, the one that I will be attaching in this video or attaching in the announcement. So this is the first question, okay? Hopefully you understood it. All right, so for question number 2, pause the video, read the question on your own. All right, hopefully you were able to pause the video, read the question on your own. And if you understand it good, try to solve it on your own. I think you can find it on LeetCode question number 101, I'm pretty sure. So if you can, try to solve it in C on your own, obviously. But if you can't, let's just decipher what the question is asking us. So the question is asking us, this time around, you're given the head of one true. Sorry, I cannot function my iPad today. You're given the root of one tree. Task at hand is to check if this tree data structure is symmetric or not. So first of all, let's understand what does it mean by saying symmetric. Let's use a highlighter. Okay, so symmetric essentially means if I were to inverse the tree, is it a mirror image? So look, so forget about the root node, because the root node is only just one node, right? So if I were to inverse just one node, if 1 is 1, 1 is 1, right? So it doesn't really matter. Forget about the root node. Let's focus on the left subtree and the right subtree. This is what we need to focus on. Now look at this. Is the left subtree a mirror image of the right subtree? It is, right? Look, I begin at 2, so look at the left subtree here. So if I were to invert my right subtree, I would get the left subtree. So this is exactly what the question is asking us. Now let's take another example here. Forget about the root. Let's talk about the left subtree. And let's talk about the right subtree. Okay, now you guys tell me. If I were to invert my right subtree, would they match? No, right? If I were to invert my right subtree, it would look something like 1, 2, 1, 2, and left child would be 3. So that's what it should look like. But it essentially is the same thing. So this tree is the same. These two, the left subtree and the right subtree, are the same, but they're not an inverted version of themselves. So this is exactly what the question is asking us. everything stays the same as the question we just covered previously. Everything, the base case is the same, checking the values the same, but the recurrence relation is the part where we need to make some changes. And I ask you this, I want you to think of yourself. In the first question, let me just try to erase this for a second. Uh, boom, 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 boom. Apologies for that. Okay, so in the first question, everything is the same. The base cases are exactly the same as they were in the first question. The only thing that changes a couple of things is, first we use a wrapper function. I don't know how many of you guys are familiar with the function, something called a wrapper function. In this wrapper function, the first, like, look, this is my wrapper function here. This is my wrapper function. In this, sorry, no. This is my wrapper function. In this wrapper function, what I do is, I take the root of the tree and I pass the left child and the right child here. So that way I'm kind of dividing my problems into two different trees, right? Because the root just stays the same as we covered, but we need the root of the left child and the root of the right child, so we can check if the left subtree is symmetric to the right subtree. So this is what I'm doing. This is the wrapper function, and in this wrapper function I will be passing the roots left child and the roots right child. So look, the base cases are exactly the same, but here now we have kind of like, let's cross this out. That means we have it, these are the values I'm passing in my the main function is valid function. So this is my left, not left height, my left child and my right child, or you can call it left subtree. Actually, let's call it left subtree. Left subtree or right subtree from this point on, right? Now look, let's draw this line. Okay, now look, if I go left here, do I need to go left on my right subtree? No, I need to go right here, right? So this is the recurrence relation part. Everything, the base case and everything is the same. The tricky part here is figuring out the wrapper function. If you guys are not familiar with it, the first time if you see it, you obviously get tripped up. But now, since we have covered it, so now you know. But the only thing that changes, you go left here, you go right here, and vice versa. If you were to go right here, you go left here, because essentially that is what I'm checking, right? I'm checking for inverted, if they were inverted or not. If left subtree is same as the right subtree inverted, then I found my answer. So the base cases are the same. The first base case, if p equal to null and q equal to null, return 1. Return 1 as in valid. If q equal to null, it doesn't really matter, but since for the sake of symmetry, I guess, null, or q equal null, return 0, right? If p's val does not match q's val, again return the value of 0. Now the recurrence relation part, let's call it function. Now if I go left, look, if I go left on p, I need to go right on q. Again, I'm using the AND operator because if at any time one of my decision returns the value of 0, I want my overall answer to be a false, right? Because that means one of the nodes does not even, that means either one of the node does not have the same value, or either the left subtree or the right subtree, they don't have the same structure to each other, right? Then AND, if I go right on P, I need to go left on Q. So this is the whole idea. This is the bulk of the end, but bulk of the work is being done. Again, one more thing I want to say: if in your final exam you're not able to figure this out on your own, try to write the base cases, right? Try to write the base cases. Try to figure out the base cases. The base cases you can figure out easily. If the recurrence relation part you cannot figure out, that's fine too. But the reason I say this: do not leave anything blank. If you write something, we as TAs are able to award you points. So that's why I'm saying this. So again, I'm not going to be showing you guys I'm not going to be like writing down the code for it and showing you how it works, working fine on my PC. I'm just going to be uploading a separate file with questions and the answers so that you're able to look at it, because this is final weeks, I'm kind of busy myself. So hopefully you understand that question. All right, so for question number 3, again, here's the question. Make sure to pause the video, read it on your own, and yeah. All right, hopefully you were able to pause the video, read it on your own. You just solved it, better, good. If you didn't solve it, that is fine. So a couple of things I want to explain first before we delve into the question. Look, in class, we have learned what? Let's draw an example. Let's do 5. Let's do 7, 10, I don't know, like 9, and then 12. All right. So first of all, ask yourself, is this what? So first of all, what is it? Is it a min heap? Is it a min heap? Or is it a max heap? All right. If you said a min heap, you're correct, right? Every value, look at the value in the root node. It is the smallest, and all the values below it are the bigger. Same here. All the values for this node, 7 is the biggest value, and all the values beneath it are bigger. Okay, so this is a valid min heap. So for a heap to be considered valid, it needs two properties. The first is it has to be min or max, right? The second is the shape property, which essentially is just the tree has to be complete. It has to be complete. And it is considered complete when all the levels are completely full, except the leaf level, and the leaf level has to be filled from left to right. So if this tree were to be like this, let's do 12. This won't be a valid min heap, okay? Because it's not complete, okay? So that's the whole point, idea, sorry. So let's do 12. So this is a valid min heap, right? So we have covered what makes a tree a heap valid or invalid, okay? So next thing, look, even though we visualize heap using a tree data structure, we always, in reality, in PA6, you guys have seen that we implement using them arrays, right? Always we visualize them, and I'll tell you the reason. We visualize them using trees because look, the left child, the right child, the left child, the right child, it becomes easier for us to visualize in our head. So this is the reason we visualize them using a tree data structure, okay? But we always implement them using an arrays. And why you think, and you might think like that doesn't really make sense. If we visualize them using a tree data structure, why not use a tree data structure to also implement it? But the idea here is, look, with arrays we get what? Fast indexing, and always start from 1, right? Let's say the value is 5, 7, 10, 9, and then 12. So if I want my left child, if I want the left child for this value, I know I can apply the formula of 2 times I. 2 times I is 2. So this is the left child. If I want the right child for this, I can apply the formula of 2 times I plus 1, which is 3, and this is my right child. So this is the whole idea. But again, sorry. Okay, so 2 times I is for the left child, 2 times I plus 1 is for the right child. If my heap is 1 based. 1 based meaning my heap starts from index number 1. If it were to start from index number 2, the formula is 2I plus 1 for my left child and 2I plus 2 for my right child. If 0 based, okay? If my heap starts from 0, let's say if we were to start from index number 0, then the formula is this, but just add a 1. That's pretty simple, and if you do the math, it makes sense. So this is the whole idea of a heap, what the heap is. I want to explain because it doesn't, if I don't explain this, and if you don't have this concept clearly in your head, you cannot understand the question. So this is why I'm taking some time to explain what a heap data structure is, and why visualize it with a tree, why implement it with an array, and this is the whole idea, okay? Now what the question is asking us, look, let me just remove a couple of values here. Okay, so this is the tree. I'll write it down later. Let me write it. So 0 based, 2I is, and then 2I plus 1 for right child, and 2I for left child. This is 1 based. 1 based, 0 based, okay? Now look, the idea is, this is a min heap. This is the tree visualization of the min heap, and this is the array implementation of a min heap, right? This is the array. Is this, look, this is a valid min heap, but this is not sorted, right? So task at hand is to, given a heap, we need to sort it. Like, look, 5 is good, 6, 7 is good, 10 is good, but 9 is before, 9 is after 10. So this is not sorted, right? We need to sort it in ascending order. So this is exactly what we have to write. So what we'll do is for this, let's say let me draw an example. So it is what? 5, 7, 10, 9, 5, 7, 10, 9, and then finally we have 12. And index number are 1, 0, 2, 3, 4, 5. Okay, so we need to sort this heap. So what we do is we will create a new memory. Let's call it res to be the same size as this, right? So to be the same size as my heap array, which is 6, right? So indexes are 0, 1, 2, 3, 4, 5. Let me just 3, 4, and then 5. Okay, so we need to sort this. So what we'll do is we create this memory, right? Second, we will loop on this array and call the remove min function. The remove min function will remove this value, replace it with 12. Okay, this is how we remove the value, right? Look, if I dequeue, or sorry, if I call the remove min function, I remove all this from the root node. And which value takes place? The last value within my tree, right? Because I don't want to interfere with my my completeness of my tree, right? So this is the whole idea. So 12 will replace it, and this remove function will automatically call what? Should it call percolate down, or should it call percolate up? What do you guys think? It should call percolate down, right? Because look, I have values beneath me to compare. I don't have values above me to compare, right? So automatically it calls percolate down internally. So we don't have to worry about that. The remove min function does it automatically. So the idea is loop through this array and at each index call. So look, the idea is to loop through this array and at each index call remove min and store the value at this index. Now we are here, and then when we percolate down, we go to 7, right? And then remove this value. Again, 12 will take its place. We percolate down, we go to 9, because 9 will become the new root, because when we percolate down automatically. So it would be what? It would be 12, 9, 10. When I percolate down, what should take place? 9 should take place of 12, right? Because this is the smaller value between these two nodes. So it would be, after percolating down, it would be 9, 12, 10. And then 9 would go here, same idea. When I remove 9, 10 would take its place. 10 would take its place, and then 10 is again is in the correct position, so I dequeue the value of 10. Then finally I dequeue the value of 12. So this is how, and now if you can see, this is sorted. So this is the whole idea of heap sort. I covered what a heap data structure is. I covered why we visualize it using a tree data structure, but why we implement it using an array, because array has what? Direct indexing, fast lookup, O of 1 lookup, right? So that's the whole idea. I covered heap sort. I covered the left child for left child, right child for 0 based, 1 based, and then let's do the runtimes. In the question, the runtimes. Okay. So look, first question is, so first of all, you need to understand what heapify is. Heapify is essentially a function that takes in an array in random order and then makes it into a valid min heap or a max heap depending on how you have implemented the heapify function. So the question, this is asking us like building a binary heap from an unordered array of size n. What is the time complexity for this? Thus, it is n. And the reason for this is n is, let me draw a small example. Again, this is a long question, but we need to nail this question, because if you understand this, then it is easier, because you need to understand it, the coding part comes naturally. Okay, so this is just random. Let's take it 10, 20, 13, 1, 7. So heapify internally calls, it starts from the first non-leaf level and then it calls percolate down. The reason it does not begin from the leaf level but from the leaf level, because I don't have any values below for me to percolate down to, right? So this is why it begins from the leaf, not the first non-leaf level, and then it calls percolate down internally. And then, since look, for each node, I am closer to the root node, right? So look, this node is the bottom level. I don't have to call percolate down on this, right? So I begin from the first non-leaf node. Then I work all the way till the root node. Since the distance to the root node is like almost cut in half, this just becomes O of n runtime. Again, you can do the math behind it or you can look it up, but it is O of n, and this is how I understood it, and it has worked for me so far. So hopefully it doesn't cause any issue later on, right? So, but this is exactly what it is. So okay, now inserting an item into a binary heap with n items. So for this is just log n. Again, when I insert an item, let's do it again. Look, Let's say this. 1, 2, 3, and let's do 4. When I insert an item, let's say I want to insert the value of 4. I insert always at the leaf level, right? And then I call percolate up regard. Let's say the value here was 0. So 0 should be the root node, right? So then I call percolate up, and percolating up all the way to the root node, the time complexity is log n, because the height of the tree or the height of the heap is log n, because the heap is complete, right? For the height of a complete tree is always log n. So this is log n. Again, same here is log n. Again, understand why it's log n, because whenever, look, oh, actually I should have taken the same example, but it doesn't matter. Okay, let's say this is my min heap. Again, I want to remove the minimum value. I remove this minimum value, and 4 takes its place, right? So be 4. Now from this, I need to call percolate down. Since the height of the tree is per log n, the time complexity is also log n. For heap sort, the time complexity is n log n. And the reason it is n log n is because, look, this is my heap array. It has n, this is the size of my heap array, which is n, right? It has n items. For each item, I'm calling remove min, or the delete function, essentially. The time complexity for the delete function is log n, and since I'm calling it for n many elements, it just becomes n log n. So that's the whole idea. Hopefully, again, don't memorize the runtime. Try to understand the concept behind it, and then it becomes very easy. So hopefully you were able to understand this question. All right, so for question number 4, we have a try question. And the idea for this question is pretty straightforward, actually. I would say this is definitely one of the easier question for tries. So first of all, we need to understand the motivation behind tries is like the reason why we use a try data structure or not a binary search tree like we did in PF5 is because let's say we have a binary search tree, let's call it BST. Let's say we maintain string 1. Let's say we maintain, yeah, string here, and then string here. The problem with that, maintaining strings in a binary search tree is what? At each node, I have to run string compare. And the time complexity for string compare is O of n. So this is bad, right? And at worst, the height of the binary search tree can be n. So it's just like n squared, essentially, right? So this is really bad. So this is why we don't want to do this, right? At each node, we have to run string compare. The time complexity for string compare is O of n. And then based on that, we go left or right. And at the very worst case, the height of the binary search tree could be O of n. So this is a bad idea, right? So this is why we don't use a binary search tree to maintain the like strings of character or strings, right? This is why we use something like a try. The time complexity for try is O of k, where k is the length of the string that we're looking at, right? So try is way better. A try data structure is essentially a node. In this node, we have 2 components. The first could be like a Boolean value, like a flag that represents like, hey, this is a valid word within my try. And the second variable is a try array of size 26, a try node array of size 26, because from 0 to 25, A maps onto 0 and Z maps onto 25. So this is why the reason it is 25. So with that being said, first of all, let's identify how many words I have within this try. The first word I have is A, B, C, D, A. Again, doesn't make sense. It does not have to make sense. As long as this variable is 1, we're good to go. Second word we have is BAD, bad. The third word we have is catch, CATCH. Task at hand, what the question is asking us is identify all the strings that are of length 5. So this is of length 5, this is of length 5. So we should return the value of 2. So this is what we have to do. Again, so what we do, first of all, we check the root node, right? We're at the root node. We check if the root node is valid or not. I mean, null or not, sorry. If the root node is null, we can just return the value of 0. And this function takes in 2 arguments here. Again, this is the concept of your wrapper function, okay? So get good with this because they might hit you with this in the FE, okay? So we're passing the root and we're passing the value of 0, which is just k. So k starts from 0, and this will help us later on. So we first verify we have the root or not. So we have the root, okay? Then we loop in this array. Look, where did I go? So we loop on this array from 0 to 26, and at each index I'm checking if it is a valid path I can take. If it is a valid path I can take. If it is, we take it, right? If it is, we take it. Again, when I do take a valid path, I increment the value of k by 1, k by 1, k by 1. So k here is from 0, now it becomes 1, becomes 1, becomes 1. Because it started from 0, right? At each decision, we are incrementing it by 1. So the value of k is 1. Again, take the path, 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 take the path. Keep taking the path until I hit a null node. For this, like I'm able to follow all the way till B, C, D, A. Eventually, once I keep incrementing my k by 1, eventually it will become 5. When it becomes 5, we can just dereference this value part here and add it to my result. So this is the whole idea. Again, I'm not coding it up because it will take much of my time and I'm kind of busy myself. So, but the coding would be all provided here. The only other concept that you need to keep in mind is we will initialize a res variable to be 0. This res variable is in charge of, well, not making the function call, but is in charge as in like whenever k becomes 5, when we dereference this value, this one value stores in res, and we do res plus, so we do something like res plus equals to the function call of whatever, or like the function call, and we pass in the root and k plus 1. So once k becomes 5, we dereference this like a boolean flag, as in like, hey, it's a valid word, and then that value is stored within my res variable. So this is the whole idea. Once you see the code for it, it becomes very evident. But again, this is really, I would say this is like a definitely an easier question for tries. Usually you're able to, they probably hit you with like something a little bit harder. So make sure to practice the prefix, because this is actually one of the main reasons we use a tries, because we want to find the prefix. This is like one of the main reasons. There's something called suffix tree, but again, that is like a more advanced topic. I don't think this is even taught in CS2, but this is the prefix. This is what we're interested in. So make sure you polish up on that. And yeah, again, the more questions you solve for tries, you better get. So you better, the more questions you solve for tries, the better you get at it again. So yeah, hopefully you were able to understand it. Okay, so for question number 5, what we'll do is, there are 2 ways they can give you a hash table question in your final exam or in your FE, right? So the first way is they just give you the formula, right? They can give you like, hey, the hash function, the formula is something like 5x plus 11 mod it by 10 by the table size. So they could give you something like this, and this is easy. You just plug in the values and do the math and calculate it, right? One other thing they can do is they could give you the hash function itself. It is up to you to decipher. Let me just zoom in. It is up to you to decipher what the hash function does and calculate the values. And always look in the question whenever there's a collision, what is the technique they're using. So in this question, they're using quadratic probing. Again, what are the collision handling techniques we have learned? Linear probing, quadratic probing, bucket hashing, separate chaining, and then double hashing. 5 techniques we have learned. So clearly in your mind, you should have them. You should understand what each one of them does, okay? Okay, for this, in this case, quadratic probing is pretty simple. Anytime there's a collision, we just apply the formula of I plus 1 squared, I plus 2 squared, I plus 3 squared, and so forth until we find an open spot. So that's the whole idea, okay? Okay, so this is what we're gonna do. So for this, we just calculate the values one by one, and then we will calculate the value for, look, hold on, let me zoom in. So we'll calculate the value for A, calculate the value for B, add the value of A plus B, and mod it by the table size. Again, table size is what? 10. And the reason I say this is not 9 and 10, I know you guys know this, but I still want to reinforce this idea in your mind, because what can happen in the final and the FE, that these are very lengthy exams, right? They're lengthy exams, so it's easy to mess up. You can just say like, hey, I just saw this 9 and the table size is 9. But since it goes 0 from 9, the table size is 10, right? 0 through 9 is 10 numbers. So again, I know you guys know this, but I still want to reinforce this idea in your head, okay? Because it's a lengthy exam, easy to mess up. All right, so what we'll do, let's just calculate 2,555 first. So A is 2555 mod 100 divided by 10. So look, this is easy actually. Anytime you have 100, 10,000, you don't need to mod it the whole digit. Just take the last 2 digits, right? And match it with the zeros. So actually I'm not doing 2,555 mod 10 mod 100. I'm doing it 55 mod 100, right? So 55 mod 100 is just 55. Divided by 10 is 5.5. Since hash table, look, for hash tables, the hashing function should always generate an integer value, right? It cannot generate a floating value or a string because the the index itself of a hash table are integers, right? So that's the whole idea. Again, this is 5.5, so it becomes 5 because it's integer division. For let's just assume it was 5.9. It also becomes 5, okay? Because that is how integer division functions. We always we always floor the value, okay? So value of A is 5. Now let's do B. 2555 mod 10. Again, I'm not doing 2555 mod 10. I'm just doing the last digit because those match, right? So it is just 5. Now the value of A is 5. Value of B is 5. Modded by the table size, which is 10. So 10 mod 10, again, is just 0. I'm not doing 10 mod 10. I'm doing 0 mod 10, right? So which is 0. So it goes here. Sorry. So it goes 2555. All right, perfect. Now let's do the second digit, which is what? 1523. So A is 1523 mod 100 divided by 10. Again, 1523 mod 10, I don't do this. I do 23 mod 100, which is 23 divided by 10, which is 2.3, which is just 2. B is 1523 mod 10. Again, I'm not doing 1523 mod 10, I'm just doing 3 mod 10, which is just 3. So value of A plus value of B mod the table size. So which is 2 plus 3 mod 10. So 5 mod 10 is just 5. So I insert the value of 1523 at index number 5. So 1523 at index number 5. Now let's do this quickly. 5893. A is what? 5893 mod 100 divided by 10. Okay, so 93 divided by 10 is 9.3, so it is just 9. Value of B is 5893 mod 10 is just 3. Okay, I'm doing this 3. So 9 plus 3 is 12. 12 mod 10 is 2. So insert the value of 5893 at index number 2. It is free, just insert it. 5893. Okay, now let's do 800. Question, no, not question number 4, but 800. So A's value is what? 800 mod 100 divided by 10. So which is, this is 0. 0 divided by 10 is 0. B, this is again 0. Again, look. 800 mod 10 is just 0, right? So I'm just doing 0 plus 0 mod the table size, which is 10, which is 0. Now look, at index number 0, we have a collision, right? At index number 0, we have a value that lies already. So we apply our quadratic formula. In this case, it is 0 plus 1 squared. When we do this, actually, we just find the first open spot. So I can just insert the value of 800 here. Okay, now let's do 956. Last value is 956 for A is equals to mod 100 divided by 10. So it is 56 mod 100, which is 56. 56 divided by 10 is 5. Okay. B is 956 mod 10. 956 mod 10 is 6. So we just do 5 plus 6 modded by the table size, which is 10. So 11 mod 10 is 1. Okay. So we need to insert the value of 956 at index number 1. Look, but this is a problem here. This is a collision, right? So we need to apply our formula. Let me just erase this. So this is a collision. So I need to apply our formula 1 plus 1 squared. So this is 2. Again, there's a collision. Okay. 1 plus 2 squared. Okay. So this is 4 plus 5. Okay. At index number 5, collision again. Okay. Let's do it one more time. 9, 10. Okay. Look. 3 squared is 9 plus 1, 10. Okay. So from this position, I will count 10 pluses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is again a collision. Cannot insert a value here. Okay. Now we have to do 1 plus 4 squared, which is 17. From this part, I will count 17 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it should go here, right? So that's the whole idea. Okay, so for the last question of AVL trees, let me just redraw this tree first. I have to switch this way because it's gonna take a lot of space, right? And let's use yellow because yellow looks bright on my screen, so I like it. So 54, 6, 3, then 4, and we're deleting the value of 8, so I'm not even gonna draw it. 76, 61, 85, 55, 67, 79, 93, 88, and then 97. Okay, so again, we need to calculate the balance factor. Okay, so first of all, what is the motivation behind using an AVL tree? An AVL tree is always balanced, right? An AVL tree is always balanced, and the reason is it is balanced because we always maintain our balance factor for each node. Balance factor has to be 0, -1. Sorry, it should be -1, 0, and 1. If the balance factor is outside of this values, the tree is not balanced. And how we calculate a balance factor for a node? It is essentially the left sub height versus the right, minus the right sub height, right? If it is not within these values, it is considered unbalanced, okay? So this is a method I learned when I took CS1, and I'm not sure if there's another method you learn, but that is fine. If you learn another method in class, please use that. But this is the method that I learned in class when I took CS1. So, and this is, I understand pretty well. So once we deleted the node 8, we need to calculate the balance factor for 6, right? The balance factor for 6 is what? Look, the balance factor for 6 is the left height excluding 6, right? So excluding 6. So essentially you can think of the left subtree height. So these two nodes. It is what? 1. 1, sorry, not 1, not 1. 2. What is the right sub height? Since there is no node here, so it is just 0, right? So 2 minus 0 is 2. So this is unbalanced. 6 is unbalanced. So we need to balance 6, right? So let me just remove this. So we need to balance 6, right? So this is the method I learned. I had learned the ABC method, where B is the middle value, A is the smallest value, and C is the biggest value. So the middle value is 4. The biggest value is C, and the middle value is, A. The smallest value is A. Right? So this is how I learned it. Let me erase this. This is how I learned this in class. So now I'm going to use the ABC method. B is the root node, A is the left child, and C is the right child. So B is the middle value, A is the smallest value, and then C is your largest value. Right, so this is how I learned it, but when I was teaching in class, a lot of people got confused. But again, with AVL trees, make sure to solve as much questions as possible. The more questions you solve, the better you get at it. And also, this is one of those topics where you should aim to get 100%, because this is a non-coding topic, and if you're someone who's struggling with coding, try to get 100 in this, because this is your free points in my opinion. So now 4 is the middle value, A is the smallest value, and then 6 is the biggest value. Now you see this is a binary search tree as well, right? So again, one way to verify your final answer is like the AVL tree should also be a binary search tree, okay? So as you can see, all the values to my left are smaller, all the values to my right are bigger. So this is a binary search tree as well, right? So let me just do this. 61, 85, 85, 79, 93. Oh, I made a mistake, right? Yeah, sorry. So it should be 79, 93, and then 88, 97, and then 55, 67. Now look, now again I need to calculate the balance factor for node 54, right? The balance factor for node 54 is what? What is the left height? Left subtree height is 2. What is the right subtree height? 1, 2, 3, 4. So I do 2 minus 4, which is what? -2. So it is unbalanced, right? So I need to balance this again. Again, for deletion, is kind of, well, not tricky, but for deletion, you kind of like, since I deleted my node from this side, so I'll go to the opposite side. So that's the whole idea. I deleted node from my left subtree, so I mark my ABC going right. So I'm gonna mark my ABCs. So ABC, A is the smallest value, B is the middle value, and then C is the largest value. Right? I'm also getting confused myself, but this is the whole idea. So again, make sure to practice this. I haven't practiced AVL trees in a while. So again, I'm just gonna make my B my middle node 76, A my smallest node 54, and then C as my largest node. Now look, the problem here, the tricky part here is, so A is 54, A is A's left child is 4, so 3, 6, that is fine. But where does this value 61 go? It cannot go to here, right? Because 61 is smaller than 76, so we copy it over here. 61, 55, 67, then 85 is just 79, 93, 88, and then 97. And as you can see, for 76, the left height is what? Sorry, let's do the balance factor. The balance factor is 3. Balance factor is 3 minus 3, which is 0. So this is valid. So that's how I do it. The only thing that you need to keep in mind is like, look, like you can also do this method like T0, T1, then so you can do like something like T0, T1, T2, T3, T0, T1 are part of A, and T2, T3 are part of C. So this is how you can do another method. So as you can see, T1, which is part of A, so it goes here. And another thing that you can do, this is kind of like the skipping part, like I just do it because I've been doing trees for so long, is that if this has a left child, look, and when I rotate this, 76 takes its place. But for 76, I already have a left child 54, so 61 just becomes this child for the right child of 54. So again, this might be a little tricky. I probably didn't do a good job at explaining this, but if you do a couple of examples on your own, and if you rewatch the recording that Dr. Ali or Dr. Rahman made, you should be able to figure this out and try to get 100 on these topics. So try to get 100 on AVL trees, try to get 100 on hash tables, because these are your free topics, okay? Good luck.